Hey everybody, welcome into this lecture, number 29 of the semester on the Lotka-Volterra model. This is a model for population, so a population model that takes into account predator and prey relationships. So this is a predator-prey model. And so let's get to it. As an example, to build this model, we're going to pretend that we have two populations. One, which will be the prey, will be the rabbits, and then the predators will be the wolves. So let's give some variables here to define our model here. So let's say R equals R of t. This is the rabbits. All right. And W is equal to W of t. This will be our wolves. So our population of wolves. And if we are to suppose that, let's first just consider the two populations separately. So in the absence of any predators, we can assume that the rabbits will be able to feed themselves on vegetables or vegetation or something. So in other words, rabbits are not predators themselves. So in the absence of predators, then the rabbit population will, we can assume that it will grow unchecked. So it'll grow in a exponential growth model. dRdt is equal to k times r for some positive growth rate, k. And then similarly, if the wolves have no food, so in other words, in the absence of prey, if we switch this around, right, and we say, all right, let's suppose that there are no rabbits and there are only wolves, in the absence of prey, then our wolf population will actually decrease. The population will decrease in an exponential growth model, where again, I wrote it this way so that we can see that it's decreasing clearly, and we'll say r is greater than 0 in this case, but the minus sign takes care of the decreasing. So the real question becomes, how do these two populations interact with each other? And interact is the key word, because when the wolves and the rabbits actually interact, you can imagine the interaction. It's not going to be pretty, right? So the wolves are going to try to catch the rabbits. Sometimes they will, sometimes they won't. And so we want the model to reflect that, right? So the more wolves there are, the more possible interactions there are with the rabbits. The more rabbits there are, the more possible interactions there are with the wolves. And then obviously if they're both growing, then there's a whole lot more chances for interactions, okay? So the Lotka-Volterra model, the way that it factors in all these different interactions between the rabbits and wolves and the two populations of these two opposite, species here, is to add in factors to this differential equation that factor in the terms that are proportional to the term of r times w. So we'll say this is the LV model. I've got it written here, so I won't rewrite it. But the Lotka-Volterra model factors in a term of this kind, so r times w, to each equation in the model. And I'll write down what the equations become then in a second here. All right, so what does it end up becoming? So these will be the Lotka-Volterra equations here. They're going to be pretty much the same thing here. The interactions, though, when the rabbits and the wolves do interact with each other, then this r times w term, again, this is always going to be positive because we're talking about populations here, right? But this is going to cause, the interactions are going to cause a net decrease in the population growth rate, right? Because some of the rabbits are going to be, unfortunately, picked off by the wolves. On the other hand, the interactions are going to cause an increase in the wolf population, in the growth rate of the wolf population, because it's going to sustain them. That's going to be where they get their food, right? And so our two equations, we now have two differential equations. They are that dr by dt, the change in the rabbit population with respect to time, is equal to k times r minus lowercase a times rw. And then dw dt, the rate of change of the wolf population, is minus little r times w plus b times r times w. And so in this scenario, all of these constants, k, a, r, and b, are all positive. So a, b, k, and r are all positive constants. Okay, and this is called the Lotka-Volterra population growth model. So that's step one. We now have the model. Now, this is a model that has two differential equations that are what we call coupled. So you can't solve the equation for r without knowing something about w, and the same thing's true about w. So you can't solve the equation for w without knowing something about r. So these are called coupled differential equations. So coupled is the definition here. And the problem is that we cannot actually find explicit formulas for the solutions, so for the populations, so for R and W, without knowing one of them. And we don't know, the whole point is that we don't know either of them, right? So instead we must think of other ways to try to get some information about the solution of this system. This is now a system because there's two differential equations, right? So we want to try to explain the solution of the differential equation without maybe actually finding it. And this is something that you'll do in applications in real life all the time. So here's what we'll do. So we'll do this a couple different ways, but instead we'll try to find, or we'll investigate, we'll look at some special solutions. So we'll investigate special solutions. Now the first special solution is probably one that you might, if you had enough time, that you would guess. The first special solution that we can think of is the equilibrium solution. So what's going to be the defining property of the equilibrium solution? It's got to be the solution where nothing is changing, right? Equilibrium means that there's no changing. So the equilibrium solution obeys, now both of these differential equations are going to be in equilibrium, so it obeys the following criteria, right? That dr by dt is equal to 0 and dw by dt is equal to 0. So these are going to be the population sizes for r and for t. They're going to be constant solutions, obviously, right? If the derivative equals 0, then r will be constant, w will be constant, and these will be the populations which sustain the numbers of the populations that sustain both populations of rabbits and wolves simultaneously. So let's look at this for our equation. Well, let's look at an example, and we'll do this example in a couple different ways. So this one we'll look at. So here's our example. I'm just going to plug in some numbers for k, a, little r, and b, and we'll see what we get here. But I'm going to write this now slightly differently. Well, I was going to write r prime, but I don't want to do that. It's very important that these are parametrized, right? That the independent variable is the same for each of them, but different than either of the two populations. So we'll say that the first equation is dr dt is equal to 0.08r minus 0.001 times r times w. And meanwhile, dw by dt is going to be negative 0.02 times w plus 0.00002 times r times w. All right, so again, we set the equilibrium solution. So we're looking for the equilibrium solution where each of these are equal to 0. This is just going to be one very, very, very special solution. I said we're going to look for special solution, plural here, but this one is just going to be the very, very special solution. And what we end up with, so for the equilibrium, let's see, the equilibrium is going to give us what? I'm going to do a couple things. So notice that in this first equation, we have an r and an r, right? So we can factor out an r. And on this equation, we can factor out a w. So the two equations are going to be r times 0.08 minus 0.001 times w. This should be equal to 0. And the next equation is going to be w times negative 0.02 plus 0.00002 r should be equal to 0. And in this scenario, obviously, if both r and w, or if either one of them is equal to 0, in other words, if there are no predators or no prey, then we just go back to this model, and we shouldn't be looking at this model anyway, right? This model with the rw term. So we're going to assume that neither r nor w is equal to 0 itself. All right, they're both non-zero. Then what do we get? Well, now we can solve the inside equations for each of these, right? We can set this equal to 0, and we can set this equal to 0. And these two equations are going to give us our equilibrium population values. So the first one says that w should equal 0.08 over 0.001, and this is going to be 80. Just move the decimals around. Okay, so there's 80 wolves, and there's a whole number, so that's good. And the other one, the second one, is going to say what? R should equal 0.02 divided by 0.00002, and moving the decimals here gives you 1,000 rabbits. So these are the equilibrium solutions. If you have 80 wolves and 1,000 rabbits, then your system's in equilibrium. Well, what's the problem with that in real life, right? So theoretically or hypothetically, that's perfectly fine. That's great. But the problem with that is that if one wolf catches one rabbit, you're no longer in equilibrium, right? Or if something happens to a wolf dies, you're no longer in equilibrium. If there's babies on either side, right, and they add to the population, you're no longer in equilibrium. So equilibrium here is kind of, we talk, when you take a course on differential equations, you'll talk about stability and instability of your equilibrium solutions. It's not super unstable here, but it's not stable, okay? So small changes in either one of these throw the system out of equilibrium. And small changes, when you're talking about animals, it's one animal in either case would throw this out of equilibrium. Okay, so there's one special solution. This is just constant functions, right? Very, 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 very simple solution here. What else could we do? So the next thing that we could try to do is we could try to look at a slope field where we compare the rabbit population to the wolf population. So we could eliminate the parameter. This is a possibility, or maybe I should say we could try to, all right, but we can do it for this one. So we can eliminate the parameter, which in this case is time, right, and consider the growth rate of one of the populations with respect to the other, right? So consider either dW by dr, so the rate of change of wolves with respect to rabbits, or dr by dW. And they should be, in some sense equivalent. So we're going to look at this one. So dW by dr. And let's see how we would do this. Well, the first thing we need to do is recall the chain rule. So we've got the chain rule. This says that, for one thing, dW by by dt is equal to, if we believe that the wolf population depends on the rabbit population, then this is going to have to be what? It's going to be dW by dr times dr by dt, the change in the rabbit population. And we have equations for these two, the outer ones, right? So we have equations for dW by dt and dr by dt. And so what we can do is, if we assume that, that the rabbit population is changing, if it's not zero, right, then we can divide through. We're not going to be able to solve this anyway in this case. So we can write this way, right? Rearranging. This is still obviously a property of the chain rule, right? So this is all because of the chain rule. dW by dr is the same as dW by dt divided by dr by dt. And so just by plugging in, if we go back to our example from here with the numbers in it, without the numbers, you can just plug in these two ratios, right? K times r minus, well, it's w on top, right? So dw dt, so you would put in this equation first, minus r times w plus b times r times w in the numerator. And in the denominator, you'd have k times r minus a times r times w. But let's do it for this example where we actually have numbers. So our differential equation would become, for dw by dr, so I'm going to write it this way. Let's rewrite the whole thing so we can get a nice look at it. But dW by dr, this is the rate of change of the wolf population with respect to the change in the rabbit population, right? So this becomes negative 0.02 times W plus 0.00002 times R times W. Again, I'm just copying down the example problem where we had the numbers in there, because then we'll talk about what we can do with such a differential equation. But the denominator becomes 0.08 times R minus 0.001 times R times W. And so now this is a differential equation that relates the wolf population to the rabbit population. Now, it turns out that this is still really difficult to solve, okay? It's not great, but what we could do at this point, so I'm going to write it this way, still can't solve it in this class, maybe ever, but you can, at least for the sake of this class, we can't solve this. And the problem here is that we haven't talked too much about this, but it's not separable and it's not linear. And those are the only two kinds of equations that we know how to solve right now, right? So separable and linear, it's neither, and you can check that yourself. So it's obviously not linear because we have these products of r times w, but it's also not separable. So let's leave it here then. So it might actually be separable if you're very careful, but we're not going to solve it, okay? What I would like to do then, instead of solving it, so I'm going to put a question mark here, and actually a recommended exercise if you want to try to solve this thing, look at this thing a little more carefully. It might be separable. But anyway, I don't want to solve it as a separable equation. What I want to do is look at the slope field. So to get the slope field, I'm going to go to Sage Math. I've got another window open here. And we looked at this in the numerical method lecture. I've already typed in everything here. So I've defined the variables r and w. I've got the right-hand side of our differential equation, this ratio. So negative 0.02 times w, etc. You can check this. It's going to be okay. And then plot slope field. So I put the range for the r to go from 0 to 3,500 and for the wolves to go from 0 to 200. Let's see what it gives us. And it takes a second, and there's a nice slope field. So here we go. I'm actually going to try to copy there we go, copy the image and put it over here so that we can look at it here. Okay, so here's our slope field. This is the slope field, again, using Sage. You can get this using any program that you prefer. But here we go. So there's our slope field for this. In this picture, the axes are, so the rabbits are the horizontal axis, right? So this is our R axis, and the wolf population is the vertical axis. And now when you look at this, you can see that our equilibrium solution of 1,000 rabbits and 80 wolves, remember that was our equilibrium, right? 80 wolves and 1,000 rabbits. This is in the center of a nice like swirl type shape here, right? So this is the equilibrium solution. It's just a point, right? And as you vary away from this point, you get caught in these kind of loop swirl type things. So what I would like to do now is just consider what's going to happen. So there's our equilibrium, right? That's the equilibrium. It's just a point. The equilibrium is just a point, okay? What's going to happen if, say, we started with, instead of 1,000 rabbits, what if we started with 50 rabbits? Oh, sorry, wolves. Instead of starting with 80 wolves, let's keep the rabbits at 1,000. Instead of starting with 80 wolves, let's start with 50 wolves. And then we would have to start about here, right? So that would be our point. And now, just like we did in previous lectures, this point would have to then get kind of caught up in the flow. And it's very slowly should be kind of growing here until it gets out to like here, and then something happens around there. So I don't quite have this right. I'm just sketching this. So, but there's like a turnaround here, right? There must be, because it's gone, it's changed. Everything's changed there. And same thing's going to happen going back this way. It gets kind of sucked up and turned around, right? And then it's going to come back around and maybe come, well, they should come together, right? So I've got some issues here, but you guys can do a better job. So I'll just keep going with this one. There we go. So the idea is that it's going to end up being a closed, what we call an integral curve. So this is the solution curve for which the point 1,000 and then comma 50. So 1,000 rabbits and 50 wolves is going to live on this curve, right? And so as time goes along, if this was, say, the starting point, as time goes along, this thing, the populations are going to kind of, the rabbit population is going to kind of boom for a while. And then as the wolf population goes up, the rabbit population is eventually going to reach a peak, right? Around, I don't know, this is about 2,750, right? Halfway between 2,500 and 3,000. And then it's going to turn back around. The wolf population will continue to increase, but the rabbit population is now decreasing, right? So that we're going back this way, decreasing R, but we're still increasing in the W direction until we reach another kind of critical point here where everything turns around again. And now we're still losing rabbits, right? We start losing wolves as well, because now we have less than the adequate amount of food. And so this will come back down, and then eventually so now what's happening? Wolves are decreasing, rabbits are decreasing, but eventually the rabbit population will start to pick back up, right? And then we'll keep going around and around and around on this vicious cycle in some sense, right? So this right here, this integral curve, describes how the rabbit population and the wolf population are related to each other. But we can try to plot these both on a time scale now, because we eliminated the time parameter. Remember, that was our whole, we eliminated t, the time parameter, to get this picture. All right. And so at this point, we can try to put it back in, right? So we can say, all right, as time increases, what happens to R and W separately? So let's say that we have, we'll call this point T0 corresponds to our starting point. And then let's at least plot these kind of important critical points here. So T0, T1, T2, T3. So we'll break this up into, we've got our T0, T1, T2, T3, and then this is all going to repeat again, right? Because it just goes around and around. So whatever shapes we get, it's going to repeat. And let's start with our rabbit population. So our rabbit population is going to start at 1,000 and go up to like 2,750. So it's going to start by increasing, right? So let's say this is 1,000, which would make this be 2,000. And then somewhere around here be 3,000. All right, well, it's going to increase pretty slowly, actually, right? This is a pretty slow, in the R direction, this is a pretty fast increase. So it's increasing pretty fast up to here. My scale is going to be a little bit off, right? But then what's going to happen? It's going to decrease. This is a slow increase, I guess, compared to this. So right here you see this looks like a more steep increase, right? So this time scale does not have to be evenly spaced. So you can kind of maybe figure out how you want to plot this yourself, but you see that around, this looks like it's very symmetric, by the way. At around 1,000 again, it's going to start, that's where the next critical point is going to be, right? So it's going to come back down, right, to here, and then it's going to keep going to here, and then it's going to start going back up again, right? And then it's going to repeat this whole process. So this is what the rabbit population is going to do, kind of, right? Pretty much. What about the wolf population? Well, the wolf population is doing the opposite, right? So the wolf population is really slowly growing from 80 up to, this looks like about, from 50 up to about 80. So now we're way down here, right? So here's our 50. So, and this goes up to only about 150. So this one's going to grow it's going to be much smaller down here, right? But again, this one kind of, how's it going to change? It increases, so the wolf population is going to increase, right? Increase, decrease. So this one's going to be something like, this. It's not great, right? But this is the wolf population. So this is the idea, though, that there's certain points where everything just starts to change, right? So the increasing, decreasing, these things are kind of, it's not exactly right, but you can kind of picture how these things are changing with respect to time. As there become more rabbits, there can become more wolves. At some point, the number of rabbits decreases then because there's more wolves, and then the wolf population has to decrease as well. So the wolf population is in some sense a little bit behind the rabbit population. And by the way, these curves, this blue curve is way too high. So the blue curve was only supposed to go up to like 150. So it grows, right? And yeah. We'll just pretend this is 150. something like this. The idea, you can plot this on your own scale though. So I'm just going to stop blabbing because now I'm just very poorly sketching these graphs. But the idea though is that just by looking at this curve, we can kind of, what you really should probably do is break up this into this curve into pieces, plot the points. It's not clear what the times are though, right? The corresponding t values. So for whatever those t values are, because these don't have to be even time frames, right? It could be this from t0 to t1 could happen very quickly, and then t1 to t2 could be take much more time possibly, or vice versa for some of these other ones. But the idea though is that you can plot the slope field, you can plot the solution curves, or at least sketch them. You can look at the behavior of the individual solutions compared to each other, right? If you pick some arbitrary time values, and maybe, if possible, you can even solve this one for r in terms of w or w in terms of r, or at least get an implicit solution equation where you could plot these curves. So there's a nice recommended exercise, and we will leave it here for this lecture, but try to see if this is solvable as a separable equation. Okay, I'll talk to you guys in the next video.